So in this video, as we had mentioned at the end of the last one, we're going to talk about how to determine whether a function has an inverse, because not all functions have inverses, and then also how to algebraically find inverses. Well, first off, when do functions have inverses? Well, a function has an inverse if it is 1 to 1. And what do we mean by 1 to 1? Well, let's do a definition here. A function f is 1 to 1 when each value of the dependent variable corresponds to exactly one value of the independent variable. Now, a way to check this graphically, and then we'll also do this algebraically, as a way to check this graphically is we have another line test. It's called the horizontal line test. A function is 1 to 1, and what does that mean? It has an inverse. When any horizontal line touches at most one point on the graph. So let's look at two quick examples here of functions that are 1 to 1 and then aren't 1 to 1. Okay, so let's look at x cubed minus 1. So it's going to roughly be, not drawing it to scale, it's going to roughly look like this. And now it's a function, it clearly passes the vertical line test, but then if I draw any horizontal line here, I touch at most one point. And so that's going to have an inverse. Now let's look at another one here. And let's say that this is, I'm not even going to write the equation down for this, but some parabola here. Real quickly, we can see this does not pass the horizontal line test. If I draw a horizontal line here, how many points am I touching? I'm touching 2. So this does not pass the horizontal line test. And so this is 1-to-1, has an inverse, and this is 1-to-1, not 1-to-1. So it doesn't have an inverse. Now we'll come back to this parabola example in a second, because there are ways to kind of force a function to be 1-to-1 if it's not. And I say kind of air quotes here, force it. We're not really forcing it, we're just going to only consider specific portions of the function. Okay, so how do we do this algebraically? Well, let's look at both of these. Let's look at the x cubed minus 1 example here. What we do to algebraically determine 1-to-1 is we suppose f at x1 equals f at x2. Then come on, pen. Then see if x1 equals x2. If they do, f is 1-to-1. If not, we are not 1-to-1. And to show something's not 1-to-1, you really only need one example of why it doesn't work. But let's go through this here with an example. So let's look at the f at x is equal to x cubed minus 1. Show algebraically it is 1-to-1. And so what we'll start with is say, well, you have f at x1 equals f at x2. Then we'll just substitute it in. So what we have is we have x1 to the third power minus 1 is equal to x2 to the third power minus 1. And then we're just going to kind of, quote, solve this, again in air quotes, for x1 or for x2. So, of course, we could add 1 to both sides. And if we do that, we get x1 cubed is equal to x2 cubed. Now we take the cube root of both sides. Now we have to ask ourselves, when you take the cube root of both sides, do I have to worry about positive and negatives? And the answer is no. Remember, the cube root, odd roots, you don't worry about positive or negatives. And so this would just give me cube root of both sides would be x1 equals x2. So it's 1-to-1. Because I get x1 equals x2, so we're 1-to-1. Now to illustrate this for something that's not 1-to-1, we know parabolas aren't, so let's look at this. F at x is equal to x squared plus 1. Well, then we'd say, just like we did before, f at x1 equals f at x2, and then that's what's saying is x1 squared plus 1 is equal to x2 squared plus 1. Now, kind of again, solve for x. So subtract 1 from both sides, and we would wind up with x1 squared is equal to x2 squared. Now, when you take a square root at both sides, remember you get plus and minus. So if we were to say x1, for instance, solve this, take square root at both sides, you'd have x1 is equal to plus or minus x2. Technically, you could say plus or minus x1, but we'll just, since we're just solving it for one side, x1 is equal to plus or minus x2, which means they're not the same value. They could be different values, because we're getting something that's saying, well, it could be positive x2 or it could be negative x2. And that's, of course, because we're squaring it. And squaring negative numbers means you get a positive number. And quickly to see what you can say is both, for instance, as an example, f at negative 2 and f at 2 both equal 5. Two different x values equaling the same y value. And so this is not 1-to-1. Now, it's a little weird doing these algebraic computations of 1-to-1 the first couple times, but actually once you get used to them, they're not too bad. All right, so we now know when things have inverses, but I said we can also, if a function isn't 1-to-1, we can kind of, quote, force it. So how do we do something like that? Well, let's look at a graph here. And I'm going to draw in x squared. So we know that this graph does not pass the vertical line test. Or not the vertical line, the horizontal line test. It passes the vertical line test. It's a function. But it doesn't pass the horizontal line test, so it's not 1-to-1. So we know that f of x is not 1-to-1. Well, what is done, and we won't be doing it in this course so much, but this is something that is going to be used in a trig course, which most of you will probably take a trig course at some point. It's called restricting the domain to get 1-to-1. What do we mean by restricting the domain? Well, the domain of f at x equals x squared. This is clearly not 1-to-1 if we look at the domain here, because the domain for x squared is all real numbers. But remember, I just need something that passes the horizontal line test in order to be 1-to-1. Now, I'm going to highlight this right half portion of this. Now, if I look at this highlighted right portion, now I clearly can see if I draw just a, well, attempt to draw what looks like a horizontal line. If I can see on the red curve, of course, it's going to hit here and here. But if you're looking at the yellow highlight, it's only touching one point on the yellow highlight. And we can see any horizontal line I'm going to draw is going to touch at most one point on the yellow highlighted portion. So what we could do is we could restrict domain of f at x equals x squared to be 0 to infinity. This is 1-to-1. Now what's important to understand here is why did we restrict it to 0 to infinity? Well, we did that just so that we have x squared. It's not the full graph anymore, but I have a piece of x squared that is passing the horizontal line test, so it's 1-to-1, and then I could find an inverse function for this piece right here. Now, I could not find an inverse function for x squared over all real numbers, but I could for the numbers 0 to infinity. So this is where domain is actually going to become very important when finding inverses. All right, so to wrap this up here, let's talk about how to find an inverse of a function algebraically. So first off, we're going to assume we have verified f has an inverse. And of course, how do we verify? We look at the horizontal line test, or we do the algebraic one-to-one test. So we're going to assume that we've already done this. So then there's kind of a set of steps here. I mean, you don't have to follow this exactly. Some books do this differently, but this is the most common practice to do, is that you replace f at x with y, then we'll swap x and y, solve for y, solve for y, and then f inverse at x is now y. Okay, so let's look at a function here, an example. We're going to do f at x is equal to (5 minus 3x) over x plus 2. We're going to find domain and range of f, find f inverse, and then find domain and range of f inverse. And we'll do that probably, we'll do 2 examples here. So, we first need to find domain and range of f. Now, I'm going to go ahead and pull a graph up here because we're going to sketch it here, because that's going to be about the only way we can really get what the range is. It's not easy to see what the range is without just sketching the function. And now we'll go into more detail about how to sketch these in some later videos here. So first off, the domain here of f, that should be easy because it's the only thing that makes the denominator 0 is the only thing we're concerned about. And so the domain of f is going to be all real numbers except x equals -2. And just to help me sketch this here, I'm going to draw a couple lines here. And so the graph of this, and I mean I could make a table and plot a bunch of different points. Whoops, that's not where that point is. So we've got 5 over 2, which is 2.5. So this is going to look like this, roughly. Okay, now you might say, how do I know that? Again, this is just very rough sketch. Been doing these a lot. Finding the domain and range of these functions is a little bit challenging, but you sketch a graph out to get an idea, and sometimes on these harder ones we might tell you at least what the range is. The domain is something you should always be able to find. Okay, so let's look at this here. Alright, well, the domain is all of real numbers except x equals -2, which this means then looking at this graph here, the range of f is all real numbers except f at x equals negative 3. I never actually get to be the value negative 3. Okay? Alright, so now we want to find the actual inverse function. So let's talk about doing that. F at x equals 5 minus 3x over x plus 2. So then finding the inverse function, there's going to be a little bit of work here. We'd have y is equal to 5 minus 3x over x plus 2. Then we're going to swap x and y. What do we mean by swap x and y? Everywhere you see an x, you're going to put a y. Everywhere you see a y, you're going to put an x. So we'd have x is equal to 5 minus 3y over y plus 2. Then we need to solve for y. So to solve for y, I'd first clear out my fraction, multiply both sides by y plus 2. And if I did that, I would have x times y plus 2 is equal to 5 minus 3y. Now I'm going to solve this for y again. So I'm going to distribute this, so I'd have x times y plus 2x is equal to 5 minus 3y. Let's move everything with a y to one side and everything with an x to the other side. So we'd have xy plus 3y is equal to negative 2x plus 5. Well, then I can factor a y out, and I'd have y times x plus 3 is equal to negative 2x plus 5. And then I would divide both sides by the x plus 3, and you get y is equal to negative 2x plus 5 over x plus 3. And so f inverse of x is equal to negative 2x plus 5 over x plus 3. Now we could verify that that's the inverse, but we're not going to take the time to do that. What we are going to do is look at the domain and range here. I'm not even going to have to do any work. If I scroll back up here, the domain of f was all real numbers except x equals 2, and the range of f was all real numbers except f at x equals negative 3. So the domain for f inverse is all real numbers except x equals negative 3, because the domain becomes the range. They flip, and then the range is going to be all r except x equals negative 2. So let's look at one more example doing this. I'm going to do the exact same thing as we just did here. So let's look at f at x equaling the square root of 2x minus 5. So let's look at first the domain and range of f. So the domain. Well, we know that 2x minus 5 has to be greater than or equal to 0 because of the square root. So 2x has to be greater than or equal to 5. So x has to be greater than or equal to 5 over 2, which we could write in interval notation as 5 over 2 to infinity. So that is the domain. Now the range here, well, remember square roots. What can I not get from a square root? I can't get negative numbers outside of there. So it's only going to be non-negative. And so the range here of this particular one would simply be 0 to infinity. Okay, so let's find the inverse. So we have f at x is equal to square root of 2x minus 5. So then you'd have y is equal to the square root of 2x minus 5. Then we swap x and y. So we have x is equal to the square root of 2y minus 5. And then we're going to solve this. Well, solve it for y. We'd square both sides, and we'd get x squared is equal to 2y minus 5. Add 5 to both sides. So you'd have x squared plus 5 is equal to 2y, which we would get y then is equal to x squared plus 5 all divided by 2. So my inverse function, I'll just write it over here, is equal to x squared plus 5 over 2. But then we have to make sure to specify what the domain and range are for this inverse function here. And well, we again swap the role of the domain and range with inverse functions. So the range of the original function is the domain of the inverse function. So domain of f inverse is 0 to infinity. Now that's really important to note here, because if we look at x squared plus 5 over 2, you might say, well, I can plug any number in. You're right, you can plug any number in. However, because we're looking at inverse functions here, you can't plug any number in the square root of x and you don't get any number out. So that very much just affects what the domain and range are for the inverse function. And then we can see that the range here would be what the domain was. And so the range would be from 5/2 to infinity, because the domain and range get swapped. Alright, so this wraps up our videos on inverse functions. And I said this is kind of our last set of videos on functions as far as general properties. We're now going to look at what I would consider our special classes of functions and do some more analysis on those.